Alright, today in Algebra 1 we're going to be taking our knowledge of exponents a little bit further. Last class period we worked with scientific notation. Today we're going to work with something called an exponential function. Now so far when it comes to graphing equations and whatnot, we've dealt with linear functions that are in the form y equals mx plus b, where we have a constant slope and a y-intercept. Now today, when we're dealing with exponential functions, it's going to look something like this: y equals a times b to the x power. Now you're going to know that it's an exponential function when that x variable is in the exponent position. So here we're multiplying by x, so it's a linear function, and here we're raising it to the x power, which makes it an exponential function. Now, what's different from an exponential function and a linear function is that a linear function makes a straight line, whereas an exponential function does not. If you've seen in some movies, they'll be talking about maybe like a bacterial infection or something like that that's growing at an exponential rate. That means it's getting really, really, really big, really, really, really fast, or really, really, really small, really, really, really fast. Now, the important things about an exponential function are that our a value right here cannot equal 0, because if we multiply anything by 0, we're just going to get 0 back, so that won't work. B has to be greater than 0, which means that it has to be a positive number, and it cannot equal 1, because if we take 1 to any exponent here, we're just going to get 1, so again, that's not going to work for exponential growth or decay. Now, on number 1 and 2, we're actually going to create the function. We're going to graph it and look at what it looks like, and then talk about its domain and range. So it says graph each function, find the y-intercept, and state the domain and range. So on number 1, we have y equals 2 to the x power. Now, 2 to the x power is exponential because our variable is here where the exponent should be. First, we're going to start by filling out our table here. Now, whatever value they give us for x, we're going to put in place of that exponent. Now, if you look, we have -2, -1, 0, 1, and 2. For me, I'm not going to start with -2. I'm going to start with the easiest number that I see on there, which is 0. So when I substitute 0 in for x, I'm going to get 2 to the 0 power. And we know that 2 to the 0 power is just 1. And then I'm going to ask myself, which one looks easier to work with, the positives or the negatives? Well, to me, I'd rather work with positive exponents first. So I'm going to come down here and substitute 1 in for x, and I'm going to get 2 to the first power, and 2 to the first power is just 2. And then I'm going to come down here and substitute 2 in for x. So I'm going to get 2 to the second power, and 2 to the second power is just 4. Now I'm going to handle my negative exponent, so I'm going to substitute -1 in for 2, and I'm going to get 2 to the negative first. Now remember, I don't like negative exponents, so I need to reciprocate that base, and that's going to give me 1 over 2 to the positive first power, and 1/2 to the positive first power is just 1/2. And then I'm going to come over here to the negative second. That's going to be 2 to the negative second power. Again, please don't put these in your calculator. We can do these by hand. I'm going to reciprocate that base, and that's going to give me 1 over 2 to the positive second power. And then I can square everything inside of those parentheses. So 1 squared is 1, and 2 squared is 4. So I have my table of values. Now I just want to come over here and plot them on my graph. So I'm going to start with my easiest number again, 0, 1. Now take note and pay attention to your scale here. On our x values, on our x-axis, we are definitely counting by 1. So we have 1, 2, 3, -1, -2, -3. But on my y-axis, we are counting by 2's. So we need to be careful of where we place our values. So my first ordered pair that I want to work with is 0, 1. So I'm going to go to the 0 on my x value and 1 on my y-axis, which is in between 0 and 2. My next value is 1, 2. So I'm going to go to 1 on the x-axis and 2 on the y-axis. Then we have 2, 4. So right 2, up 4. And then we're going to have -1, 1/2. So if I go to -1, and then 1/2 is halfway in between 0 and 1. And then -2 is 1/4, so that's halfway in between 0 and 1/2. And it's going to look like this. Oops, I got those in the wrong place. Should be here. and here. Now, this is kind of a weird looking graph here because we're going by values of 2. So to get a better feel for it, I'm going to go ahead and see what x would be if I substituted in 3 for x. So if I substituted in 3 for x, it's going to be 2 to the 3rd power, which is 8. So if I go to 3, that's going to bring me up to 8. And if I put 4 in for x, that's going to give me 2 to the 4th power, which is going to give me 16, which is all the way up here. So that's going to give us a better representation of how our graph will look. As you can see, it's definitely not a straight line, so we can't use a straight edge to connect this. What we're going to have to do is we're going to have to freehand it. So I'm going to start at 0. I'm going to freehand connecting to my dots. As you can see, it's curving as we're getting bigger, and it's going to keep getting bigger at that rate. As I'm going down, again, it's curving and curving, and I'm going to keep getting smaller and smaller. Now, here's what our graph is going to look like. This is an exponential function. It is not a linear function. It is not a straight line, but it is getting, in this case, bigger and bigger and bigger. So the first thing they want to know is this exponential growth or is this exponential decay? Well, as we read the graph from left to right, it's getting bigger, which means that it is exponential growth. So we're going to circle exponential growth. Now the y-intercept, they just want to know where does our graph cross the y-axis, and the y-intercept is at 0, 1. And then they want to talk about our domain. Our domain is our x values, remember, so they want to know what possible values could we have for x. So let's think about it. For the x values, that's what we're substituting into our x variable up in that exponent. So if I wanted to think about numbers that I could and could not put in for that x value, I could put in negative numbers and 0 and positive numbers. If I wanted to, I could also put in fractions or decimals or anything like that. So our domain is going to be the set of all x's such that x is an element of the real numbers. We can choose any real number to go in there for x. Now let's talk about the range. The range they want to know is what possible values for y could I have? So when I substitute in any value for x, what am I going to get back for y? Well, we already know that this is going to keep getting bigger and bigger and bigger and bigger, so we can have any number up here that's really big, and as you can see here, our graph is filling in. We can have decimals and fractions, but let's talk about how small my number can get. If you pay attention to our graph here, when I substitute 1 in, I get 2. But when I substitute negative 1 in, I get 1/2, which is the reciprocal of 2. If I substitute 2 in for x, I'm going to get a y value of 4. But if I substitute negative 2 in, I get 1/4, which is the reciprocal of 4. When I substitute 3 in, I get 8. So if I substitute negative 3 in, I'm going to follow this pattern, and I'm going to get 1/8. If I substitute 4 in, I got 16. If I follow that pattern, the reciprocal of that is going to be 1/16. So the pattern that I hope you're noticing here is that my numbers are getting smaller and smaller and smaller and smaller. However, they are still fractions. So what's happening is my numbers will never, ever, ever cross the y-axis. I can never have, or excuse me, the x-axis. I can never have a 0 for my y value. So what we're going to do is we're going to take our straight edge and we're going to draw a dashed line right there at y equals 0. And what that's called is called the asymptote. That's like a border that our graph can never touch or never cross. So when we make our graph, it's really important that it doesn't cross that asymptote. So again, this y equals 0 is an asymptote. ASYMPTOTE. This asymptote is like a boundary that our graph will never cross. Well, that means our range is going to be the set of all y's such that y is greater than 0. And if you think about it, that makes sense, because there is no way that I could put anything in for x that would make this number a 0 or a negative exponent, because when we put 0 in for x, we actually get 1. So here we have our first example of an exponential function. And as you can see, we consider this to be exponential growth. It has a y-intercept of 0, 1, and it has a domain of all real numbers and a range of y is greater than 0. If we go to 2, Again, they want us to do the same thing, so we have y equals 1/4 to the x power. Since our variable is where the exponent should be, that's a huge indicator that this is an exponential function. So I'm going to start with the easiest number on my chart. If I substitute 0 in for x, 1/4 to the 0 power is just going to give me 1. If I substitute 1 in for x, I'm going to take 1/4 to the first power, which is just going to give me 1/4, and let's leave it as a fraction because they gave us a fraction. If I substitute 2 in for x, that's going to give me 1/4, and that's going to give me to the second power. So 1 to the second power is 1. 4 to the second power is 16. So I'm going to have 1 over 16. Now, if we follow the pattern that we did on number 1, when I take 1/4 to the negative 1 power, that's going to take this what I got for the positive 1 power, and just reciprocate it. So that's going to give me the reciprocal of 1/4, which is just 4. And then same thing goes with negative 2. I'm going to take what I got for 2, which is 1 over 16, and reciprocate it, which gives me a positive 16. So now we want to put this and graph this on our graph. Again, take note that our x-axis has a scale of 1 and our y-axis has a scale of 2. So if I start at 0, 1, it's going to be right here. And then 1, 1/4 is going to be about right here. And yes, you can estimate. It might not be exact. It's going to be an approximate. And then 2, 1/16 is right here. Negative 1 is going to be at 4, which is right here. And negative 2 is going to be at 16, which is right here. So again, we have a very clear exponential function. We're going to have to approximate when we draw it. Now I'm going to connect those, and we know it's going to get smaller and smaller. And we'll connect those, and it's going to be on a curve. And it's going to get bigger and bigger. That's kind of a bad curve there, but that's okay. It's freehanding. All right. Now we want to talk about, is this exponential growth or exponential decay? So as I follow my graph from left to right, it's getting smaller, which is the indicator that it's going to be decay. It's decaying as it moves on. My y-intercept is where it crosses the y-axis, and that is still at 0, 1. My domain is all possible x values that I could get. So all of my x values, all the numbers that I could put in for x, are just going to be the real numbers. So set of all x's such that x is an element of the real numbers. And then again, my range is what possibilities I could get for my y-axis. So if I look at my y-axis, if I look at my y values, I'm going to notice that I'm getting smaller and smaller and smaller. But again, as you can see, we're not touching that y equals 0, and we're not crossing that because I can't put anything in for this variable right here that will give me a negative number or a 0 back. So that means there's going to be an asymptote at the y equals 0. So let's draw that in as a dotted line, and we're just going to write the formula, or write the equation for that line, y equals 0. Again, that's our asymptote. That's our boundary that we never cross. And that means that our range is going to be the set of all y's such that y is greater than 0. Alright, so as of right now, you guys have graphed your first exponential functions. If we take a look at number 1, we saw that it was exponential growth because it was getting bigger, and number 2 was exponential decay because it was getting smaller. But even if it's exponential growth or decay, they both had the same y-intercept, they both had the same domain, and they both had the same range, which means that they both had the same asymptote. So the only thing that's going to be different is whether it's decay or growth and the actual numerical values for what we're plotting. Now, there is actually a trick to make it easier to see if it's exponential growth or exponential decay without graphing your graph. If we look at number 1, we know that it was exponential growth because we graphed it. But if we look at the number that's being raised to the exponent, this 2, we can tell that it's greater than 1, which means that it's going to be exponential growth. On number 2, we're taking 1/4 to the x power, and 1/4 is between 0 and 1, which means that it is a fraction or a decimal, which means that it's going to be exponential decay. And if you'll pay attention, that's going to happen pretty much every time. So on number 3, they're saying, given each function, answer the questions provided. So we have 1, 2, 3, 4, 5 questions that they want us to answer, and we just have to fill in the chart. I'm not going to make you graph it because I feel like you guys just need to know more about it than be able to do it. So on number 3, we have y equals 3 to the x power. We know right away that it is an exponential function because our variable is where the exponent should be. And they just want us to fill out a table of values. So just like we did on number 1 and number 2, they give us an x value of 0, and I'm going to substitute that in for x. 3 to the 0 power is 1. They give us an x value of 1. 3 to the first power is 3. They give us an x value of 2, so 3 to the second power is 9. And then we're going to go to the negative exponents. 3 to the negative first power is going to be the reciprocal of 3 to the first power, so that's going to be 1 over 3. 3 to the negative second power will be the reciprocal of 3 to the second power, which is 1 over 9. So part B says, is this going to be exponential growth or exponential decay? Now, you could look at your chart and figure it out from there, see if it's going up or down, but all you have to do is look at this number right here. It's bigger than 1, so it's going to be exponential growth. All right. Letter C says we want the domain of this function, but before we do C and D, I'm going to skip down to letter E, and this is going to seem like we're going in a backwards order, but that's okay. Once we pick the graph for this function, it's going to be easier to choose the domain and the range. So we want to choose the correct graph to represent this function. Since we know it's exponential growth, we want to choose the graph that's getting bigger from left to right. So on letter M, our graph is getting bigger from left to right, and on letter N, our graph is getting smaller from left to right, which means that since it's exponential growth, the graph to represent this function is letter M. And now we can go back, and it's a little bit easier to see our domain and range. Our domain is all of our x values, and since we can sub any number in for x, our domain is going to be the set of all x's such that x is an element of the real numbers. So if I look, that's going to be letter F. And the range, remember, has to deal with the asymptote, where we're not touching. So if you look, my graph kind of levels off here around that y equals 0 area, so our asymptote is at y equals 0, which means that my range needs to be set of all y's such that y is greater than 0. So it's going to be letter K there. All right, we can go to number 4. And number 4, we have y equals 1/3 to the x power. What I want you to do is I want you to pause the video on number 4 and fill out the table all by yourself. All right, hopefully when you fill out the table, you got -2, 9, -1, 3, 0, 1, 1, 1/3, and 2, 1/9. And let's talk about if it's exponential growth or decay. All we have to do is look at this number being raised to the exponent here, and we see that it's 1/3, which is a fraction between 0 and 1. So that means it's going to be exponential decay. Now I'm going to come down here and choose which graph best represents exponential decay. If it's decaying, it's getting smaller as we're going on, so we want our graph to get smaller as we move from left to right. Now we can easily choose the domain. The domain represents the x value, so I can choose any x value to go in there, which means it's going to be the set of all real numbers. And then the range has to deal with the asymptote. So we can look at that graph again and see that it's getting closer and closer, but doesn't really touch that y equals 0. So it's going to be the set of all y such that y is greater than 0. All right, now if we go on to number 5, this is just a little bit of a review that I wanted you guys to get some work with. It says evaluate each product or quotient, then express the results in both scientific notation and standard form. Just a reminder, please don't just put this in your calculator. We want to use our knowledge of exponents. So here we would start by taking 9.6 divided by 1.2 and go from there. What I would like you to do is pause the video and get these 4 problems done, then come back and check to see if we're on the right track. All right, for number 5, hopefully you got 8 times 10 to the 8th power, which is going to give me 800 million in standard form. On number 6, 1.6 squared is going to give me 2.56 times 10 to the 12th power, which is 2 trillion 560 billion. On number 7, when we multiply those together, we're going to get 9 times 10 to the negative 4th, which is in standard form 0.0009. And then finally on number 8, when we divide those, we're going to get 0.689 times 10 to the 4th, but that's not in scientific notation, so we need to move that decimal place over and get 6.89 times 10 to the 3rd, which is 6,890. And we can box those two answers. Now, what I'd like you to do is I'd like you to get out your homework, and we're going to do the first couple of problems together. So on your homework, on number 1, it says graph each function, find the y-intercept, and state the domain and range. This is just like we did on number 1 and number 2 on the front side of our practice. So what I want you to do is pause the video, and please just do number 1 on your own. Alright, hopefully when you finish number 1 it looks like this. We've got our chart filled out, we've got our asymptote on our graph, and it's going to be exponential growth with a y-intercept of 0, 1, a domain of x is an element of all real numbers, and a range of y is greater than 0. Now if we go to number 2, it's going to be a little bit different. It still wants us to graph and find the x and y, or find the y-intercept and state the domain and range, but as you can see we have y equals 3 to the x power plus 1. This is exponential because our exponent is where or our variable is where the exponent should be. So let's fill out this chart together. I'm going to start with 0 again. So if I substitute 0 in for x, I'm going to get 3 to the 0 power plus 1. Well, 3 to the power is just 1. And 1 plus 1 is going to give me 2. So when I have an x value of 0, my y value will be 2. Now if I go to my x value of 1, I'll have 3 to the first power plus 1. Well, 3 to the first power is 3. And if I add that to 1, I'm going to get a y value of 4. Now I have an x value of 2, so if I have 3 to the second power plus 1, 3 to the second power is 9, plus 1 is going to give me a y value of 10. Okay, now if I go to the negatives, I'm going to have 3 to the negative first power plus 1. Well, 3 to the negative first power is the reciprocal of 3 to the positive first power. 3 to the positive first power is 3, so the reciprocal is going to be 1/3. And I'm going to add that to 1, and I'm going to get 1 1/3. And I know that we usually put improper fractions, but for this lesson it's okay to do mixed numbers. Then if I have 3 to the negative second plus 1, 3 to the negative second is the reciprocal of 3 to the second, so the reciprocal of 9 is 1/9. I'm going to add that to 1, and I'm going to get 1 1/9. So now let's take a minute and let's graph this on our graph. So I'm going to have 0, 2 is where I'm going to start. Then I'm going to go to 1, 4, and 2, 10. Then I'm going to have negative 1 and 1 1/3, so it's going to be above 1, in between 1 and 2. And then negative 2, 1 1/9, so that's going to be in between 1 and 1 1/3. It's going to look like this. So if I connect my dots, got a curve going. It'll look like this. Now, let's talk about if it's exponential growth or decay. It's still growth because the number being raised to the exponent is greater than 1. My y-intercept, however, is 0, 2. My domain, I can still put any number in for x, so it's going to be the set of all x's such that x is an element of the real numbers. Let's talk about my range. My range is going to be different because of this right here. Since I'm adding 1 to the end of my function here, if you've noticed, things are kind of looking a little bit different. Here we used to just have a fraction, and now it's 1 and a fraction and 1 and a fraction. So what's happening is my graph kind of shifted up. So my new asymptote is actually y equals 1 because my numbers are getting closer and closer and closer now to 1. So my range is now going to be the set of all y's such that y is greater than 1, all because of this plus 1 at the end. So think about it. If we had a plus 2 at the end, my asymptote would then be y equals 2. My range would be y is greater than 2, and my y-intercept would be 1 more, which is 3. Okay, so now if we go to number 3, it says describe the difference between the graph from 1 and 2. Well, they still have the same exponential growth. They're still growing as we're going, but the difference is, the main difference right here is the fact that we've taken the graph from number 1 and shifted it one whole unit up. So describe the difference. Our graph of y equals 3 to the x has been moved 1 unit up. So everything that's dealing with our y values has been shifted 1 unit up. Alright, that wraps up section 7.5 over exponential functions. If you have any questions, please let me know.